warm up, please pause. Okay, so to find the equation of the line tangent to this function at x equals 2, I need a point and I need a slope. So for the slope, I need to find y prime, which is going to be 10x plus 3. When x is equal to 2, that's going to give me 23. For my point, I already know that the x value is 2. I need to find the y value. And so y of 2 is going to give me 5 times 2 squared plus 3 times 2, which is going to give me, is that 26? And so my tangent line is y minus 26 is equal to the slope, 23, times x minus 2. Or y is equal to 26 plus 23 times x minus 2. Okay, today we are going to learn a cool little topic called Euler's method. I know that you want to pronounce this Euler, but that is wrong. It is pronounced Euler, Euler's method. And it is a method for approximating solutions to differential equations. I told you before that there are lots and lots and lots of types of differential equations, most of which you don't know how to solve yet. But Euler's method is going to give you a way to approximate some solutions. So it's a method for numerically approximating particular solutions to differential equations. And in order to apply Euler's method, you need to have an initial point, and you need to have a derivative rule, which is usually in the form of a differential equation. And what Euler's method does is it repeats tangent lines. Okay? If you can find the equation of a tangent line, you can do Euler's method. All right? It's just tangent line after tangent line after tangent line. The idea is that using a given step size, we write repeated tangent lines to approximate the value close to a known point. If our differential equation is the form of dy dx equals some function of x and y, then each iteration of Euler's method is going to take the form of my new y value is equal to my previous y value plus the derivative rule evaluated at my previous point times the difference between my new x value and my old x value, and this right here is just the step size. Copy this down. This will make sense once we start doing some examples. I want to give you a visual. So say I have some curve that I'm approximating with Euler's method, and I have an initial point, and I am given the derivative of this function. I don't know it, but I know its derivative. However, I can't solve because it's not a first-order separable differential equation. What I'm going to do is write the equation of a tangent line that starts at this point. Then I'm going to go a little further in the x direction, let's say to here, and find the equation of the tangent line. It's not really a tangent line because I'm not touching the function anymore, but I'm going to find the slope at this x value and rewrite my tangent line with that slope. Then I'm going to go a little further in the x direction and rewrite it with the new slope. So it's basically taking tangent lines in little itty-bitty steps that should kind of follow the path of this function. And it's going to give me a much more accurate approximation than if I had just used one tangent line. This drawing is awful, but I'm hoping that made a little bit of sense. So if you're confused, let's try an example. We are going to use Euler's method to approximate a value for the solution of this differential equation at x equals 2 using step sizes of h equals 0.5. Okay, so this is my derivative rule. This is my initial point, and I'm told to use a step size of 0.5. Okay, so what I'm going to do, I'm going to start with my initial point, which is 1, 1. Okay, my next point, well, I'm using a step size of 0.5, so my next x value is going to be 1.5. comma, I need my new y value. I don't know it yet. Since my step size is 0.5, my next x value, is going to be 2. I'm going up by 0.5. And I want this because I want to approximate the solution when x equals 2. All it took me was 2 steps to get there because I was using a step size of 0.5. So for this one, using the formula, my new y value is going to equal my previous y value, 1, plus the slope evaluated at my previous point. My previous point is 1, 1. My slope rule is x plus y. So when the point is 1, 1, the slope is 1 plus 1, which is 2, times the change in x from here to here. But that's just my step size. Over here is always just going to be my step size, 0.5. Okay? So this gives me 1 plus 2 times 0.5, which is 2. I've completed one iteration. Now I need to complete the second iteration. y2 is going to equal my previous y value, 2, plus the slope based on my previous point. Now this is my previous point, and x plus y is now going to be 3.5. Times my step size, my change in x, which is again 0.5. Oops. I don't know what this is, but if it's free response, then by all means, leave it like that, okay? If it's multiple choice, you'll actually have to go and figure that out. But that is my approximation. That is my answer. Okay. That was the example we just did. Let's try another one. We're going to use Euler's method to approximate a value for the solution of the following differential equation at x equals 3 using 4 iterations. Now they didn't tell me my step size here. I'm going to have to figure it out. My initial condition, my initial point is at an x value of 1. And I want to get from 1 to 3 using 4 iterations. So I'm going to do the change in x, which is 2, divided by the number of iterations, 4, which is going to tell me my step size needs to be 0.5. So h is equal to 0.5 here. All right, so my initial point is 1, negative 1. My second point is going to be 1.5, something. My next one is going to be 2, something. 2.5, something. And then 3, something. And that is 4 iterations. From here to here is 1, 2, 3, 4. This is probably going to be a calculator question, I'm thinking. All right, so my first iteration is going to be the previous y value, negative 1, plus the slope based on my previous point. My slope rule is now x over y. So x over y gives me negative 1 times my step size, which is 0.5. So this is negative 1 minus 0.5. This is negative 1.5. That's one iteration. I want you to pause the video and do the other 3 iterations and get your answer. All right, for my second iteration, I get y2 is equal to the previous point plus the slope based on the previous point, x over y, which is still negative 1, times 0.5. So I have negative 1.5 minus 0.5, that's negative 2. My third iteration is equal to negative 2 plus my slope evaluated here again is negative 1. And this is going to give me negative 2.5. And my fourth iteration is equal to my previous y value plus the slope based on my previous point times the step size, which is going to give me negative 3. So I lied. This was not a calculator question. And the reason for that is that if I solve this, this is actually one that I can solve. I end up with y dy is equal to x dx, which if I integrate gives me 1/2 y squared is equal to 1/2 x squared plus c. If I multiply both sides by 2, I get y squared is equal to x squared plus c. And if I take the square root of both sides, I get y is equal to plus or minus the square root of x squared plus c. And basically, if I were to plug in this initial condition of 1, -1, then I would get, let's see, -1 is equal to, this forces this to be negative, square root of 1 squared plus c, which means I have 1 is equal to the square root of 1 plus c. C is 0. This is basically y equals -x is the solution to this. So actually, this wasn't even an approximation. This came out exact, but that's because what I gave was a very simple differential equation. Still good practice, though. All right, I want you to try this one from the beginning. We're using Euler's method to approximate a value for the solution to the following differential equation at x equals 1 using 4 iterations. So I'm going from x equals 0 to x equals 1 using 4 iterations. Pause. Okay, so this one, my initial is 0, 0. I'm trying to get from 0 to 1 using 4 iterations. So my step size is now 1/4 or 0.25. So I'm setting up my kind of chart. This is me taking 4 iterations to get from 0 to 1. And so here we go. Y is equal to the previous y value plus the slope based on the previous point. 0 plus 2y, when those are both 0, is 0, times the step size of 0.25. That gives me 0. Okay. Now y is equal to the previous y value plus the slope based on this point, which is not 0. X plus 2y is now 0.25 times 0.25, which I believe is so now y is equal to 0.0625 plus, I use the slope rule based on the previous point, so 0.5 plus 2 times 0.0625 gives me a slope of 0.625 times my step size, and that gives me 0.21875. I wouldn't round if I were you. And then this final iteration gives me 0.21875 plus the slope based on that point, which I get to be 1.1875 times the step size, 0.25. And I get a final answer of 0.515625. Or you can leave it unsimplified. That is fine. Okay, that is it. Here is your homework assignment number 3, just 4 problems. For number 73, I want you to follow the actual directions. For number 75, 76, and 77, I just want you to do 3 iterations of the given step size. I think they ask you to do like 10, and that's ridiculous. Okay, you don't need to do this 10 times to get what you're doing. So you can stop after 3 iterations. Your answer won't match the back of the book, but it'll match what I give in class tomorrow. Okay, so I'm being kind here and just asking you to do 3 iterations. By the way, on the AP exam, the most they ever have you do is actually 2 iterations because they figured that gets the point across. So just so you know, on an AP question, you'll never have to do more than 2.